Hello and welcome to the 14th lecture in the Jabrah reinforcement learning series. So today we're going to be wrapping up our discussion on the Monte Carlo algorithms by looking at the final topic, which is off policy for Monte Carlo control. And we'll also look at a couple of techniques that help us improve our algorithms, especially in the context of importance sampling. So having said that, let me jot down the topic for today's lecture. So we're looking at off policy Monte Carlo control. So in order to be able to understand the context of what we're going to be talking about this lecture, we're going to look at something else first of all before actually going into this algorithm. So it's known as incremental implementation, right? This is just a way for us to be more efficient when we're implementing our Monte Carlo algorithm, so to speak. So incremental implementation. So what are we talking about here? Because when we looked at the previous lectures, we were talking that we have a bunch of returns for a given number of states, and we attribute a certain importance sampling ratio to these returns, right? Because we're given a target policy and we have a behavior policy, and we're trying to find the value function of the target policy by sampling from the behavior policy. So this is what we talked about in the previous lecture. So most of what we're talking about here, of course, I'm assuming that you've actually gone to the previous lecture. So I'm actually going to get down to the point where if we're given Wi, right, we denote something known as Wi, which is analogous to our importance sampling ratio, which was PT up to TT. Let's use I here because we're talking about Wi. So there's a subscript I, TTI minus 1. So this is just the importance sampling ratio that we discussed in the previous lecture. We're just denoting it for Wi. And what is this I index reflecting? Well, we have certain returns for a given state. So we have return G1, we have G2, we have G I up to final some Gn for different states. So given a state, we have multiple returns. So we're trying to find what the value of that state is, right? And this is, of course, from the previous lecture. I'm just giving an overview. So if you don't remember any of this, please just watch the previous video. So we said that we estimate the value function, right, Vn, as, well, we'll look at the summation, right, from k is equals to 1 up to n minus 1 of wk gk, right, divided by the summation from k is equals to 1 up to n minus 1 of wk, right? So we had denoted this as the weighted importance sampling, let me write faster, ratio. So this is what we had called this. We say that this is the weighted importance sampling ratio. So having said that, we also talked, of course, in the previous lecture about what's the ordinary importance sampling ratio, what's the difference between that and the weighted importance sampling ratio. So again, I'm just going to skip through this since we've already covered it. So this is how we compute the weighted importance sampling ratio for our value function for a particular state. But we notice something here. Well, given this equation, we actually would have to wait until we get all the returns from the given state, and compute all the weights, and then finally when we have all the weights and all the returns, then we can find this value for this particular state. But we don't actually have to wait until we get these values. We can actually use a more incremental approach to continuously update our value function for a particular state, right? Using this importance sampling ratio. So for us to be able to do that, first we need to denote a couple of things. So the first thing I'm going to denote is something we call Cn. So Cn, we can say this is the cumulative sum, right, of the weights for the first n returns. So this is essentially what Cn is. We're just looking at while we're actually generating our return step by step for a particular state, we take the weights and we sum them up, right? So if we're summing them up, then we store them in a variable that we're calling Cn here. So essentially, our update rule, right, for this value function, we can rewrite this as, if we want to find the value at the next time step, right? Not necessarily next time step, but I should say the next time we encounter the state, right? And we want to update its value. So Vn plus 1, we compute this as Vn plus Wn, right, over Cn times Gn minus Vn for all n is greater than or equal to 1. So what we're doing here essentially, so this is the update rule, the incremental update rule for this Monte Carlo. And what we're doing is that when we receive a new return Gn, it will have its corresponding weight, which we call Wn, right? So this is essentially what we know, what we can, I can just denote this. Let me use a different color. I can sort of denote this as the new, let's just call it the contribution here, right? This is kind of like the contribution, like that this Gn has, like the difference between it and the Vn, and this is kind of like the weight, right? So in a sense, we end up having some weighted contribution of this new value being added to Vn. This is just a loose definition, of course. You don't actually, there's no literature for this. But the point here is that given a new Gn, we subtracted from the Vn this difference that we're calling the contribution, and the current Wn, right, we divide it by the cumulative sums of the weights that we have seen so far, right? So this will help us weigh the importance of this new return, of course, when we are adding it to Vn. So this is just based on the weighted importance sampling ratio that we're talking about earlier. So this is essentially our incremental implementation, or just an incremental update. Let's just go with this, right? So this is our incremental update, and then of course we would update Cn to be equal to Cn plus Wn plus 1, right? This is how we update our Cn. When we receive a new W, then we add it to our current weights. So this is essentially what incremental implementation is in the context of Monte Carlo. So to have a better idea of what I'm actually talking about here, let's actually look at the pseudocode for off-policy Monte Carlo for the control problem, right? So let me open up a new page. So we had said before, right, that when we are doing Monte Carlo, in the context of when we are doing importance sampling, we have a behavior policy and we have a target policy. And the behavior policy helps us generate behavior, how to behave in different states. And we use this behavior to update the value function for the target policy. So this is in context what we had discussed before. So now I'm just going to look at the off policy Monte Carlo control code, right, where we're actually utilizing importance sampling. So most of these concepts are things that you're already familiar with if you watched the previous video, so I'm not going to like spend too much time on this. So first things first, we're going to initialize for all states, right, for all, sorry, S is an element of S. And all actions in the action space. So what are we going to do? So first things first, we define qs comma a, right? Qs comma a. So we define this, let's just say arbitrarily, right? So this is our q values as always, and then c s comma a. So we initialize this to 0 in the beginning. So what's c s comma a? This is the same thing we're looking at when we're talking about cn is equal to cn plus this weight. So that's what c s comma a is. And then we've got pi of s, right? This is our, let me rewrite this better. So this is essentially our target policy, right? And we're going to have a deterministic target policy. We're going to say pi of s is the argmax over all actions of q s comma a, right? This is our target policy. So let me just denote it in red here, that this is our target policy. Okay, so what are we going to do? We're going to loop forever, well, until we reach some, condition. But what are we going to do? We're going to define b, right? And let's just say this is any soft policy. If you remember, you should know what a soft policy is from our very much earlier lectures. I don't remember which one it was. So this is going to be our behavior policy. That's what B is in this context. So we have B, which is any soft policy. So we're going to generate an episode using B, right? So generate an episode using B. So the episode, as usual, it looked like S0, A0, R1, all the way up to some final time step when we receive our final reward, which is our capital T. Again, something which you should be familiar with. We'll initialize G to be equal to 0, right? And then we'll initialize our W to be equal to 1. So this is what our W is in the current time step. So we're going to loop for each episode from, I guess, t is equals to 0 all the way up to some final value t minus 1 or whatever. And we're going to say G, right? We're going to assign this to R t plus 1 plus gamma times the value of G, right? This is, of course, we already know this from all the pseudocode we looked at from the previous Monte Carlo algorithms. And then we're going to update our C, right? So C for our current state, say ST and action. And we're going to assign it the value, the old C plus W. Why? Because again, we defined C as the cumulative sum of the weights for the first n returns. So we'll continue for every single time step. When we count a certain state action pair, we'll update their cumulative weights as well. And not only their cumulative weights, of course, we also need to update the Q value, because this is the meat of the problem, so to speak. So QST, AT. This is gonna be equal to the old QST, AT, right? Plus W over CST, AT multiplied by G minus QST, AT, which is our incremental update, right? So we had called this incremental update. Okay, so having done that, we move on to the next step. So of course, now that we have Q, since we're doing the control problem, we need to look at our target policy. So pi of ST, right? Again, this is the argmax over all actions, right, of Q ST, A, right? This is what we had defined our, our target policy as. So that's what pi of ST is here. So here's the condition. If AT, right, our current action, is not equal to pi of ST, then you need to exit this loop, right? And why is that? Why do we need to exit if they're different? Well, the condition is actually based on the next thing we're gonna write, and that's our update for W. We say W is equal to the old W multiplied by pi of AT given ST over BAT given ST. So this is just how we updated based on the importance sampling ratio that we defined in the previous lectures, right? So of course, as we are making those multiplications of these different probabilities of taking some action in a given state, one thing to note here is that the AT has to be the same. So the actions we're looking at from the behavior policy and the action we're looking at from the target policy have to be the same, which is why we say if for some reason this end up being different, then we need to break, because we can no longer update this current state action pair, right, using this weight essentially. So insofar as they are the same, then we can continuously update this. So having said that though, since this is actually deterministic, this pi AT given ST, so what we can do, we can actually, instead of writing it, we can alternatively write this as W multiplied by 1 over BAT given ST. And why this one? Because the probability of taking an action given a particular state under policy pi is always 1. Why? Because it's always the argmax over all actions, and it's a deterministic policy as per our definition. So that actually concludes at least this algorithm at this point. Okay, so far when we're looking at importance sampling, we were forming our importance sampling weights for returns, considering them as unitary wholes. And this can actually lead to a lot of variance in our off policy estimators. So we're going to look at some cutting edge ideas on how we can actually reduce this variance. And to give you a better understanding of what I'm talking about, let's actually look at an example. This will kind of be an extreme case. So let's say that we have a very long episode, right? So, uh, well, in general, long episodes. So we have long episodes that last, say, 100 steps, right? And we have our gamma set at 0, right? So if you remember, because we define our return gt to be equal to rt plus 1 plus gamma rt plus 2 plus gamma squared rt plus 3 and so on, right? So since this is how we define our g, if we set our gamma to 0, we're just showing that we care more about the immediate rewards and we don't really care much about those future rewards. So this is what a low value of gamma actually represents in general. So given this scenario, right, that I just described here, we'll see that let's look at the return for time step 0, g0 in here. So this will just be equal to r1, right? Because we don't care about all these future rewards since our gamma is 0. But now, since we're doing importance sampling, we're weighing our returns by the importance sampling ratio. So since we're weighing our returns by this, what we need to do is, in this example, let's actually look at what this weight, this ratio looks like. So when we're talking about our importance sampling ratio, so from p from t up to tt minus 1, so this will be pi a0 given as 0 divided by b a0 given as 0 multiplied by pi a1 given as 1. So you got b a1 given as 1 and so on up to pi a, since we have 99 steps, 99. Should have used capital A, but anyway, you get the idea. As 99, all of this divided by b a 99 given as 99. So this is our multiplication product. So let's look at ordinary importance sampling. So this return will be scaled by the entire product here, right? But we only need to scale this, right? We only need to scale this by this first term. These other 99 factors are irrelevant when we're computing G0. Why? Because G0 is only, when we're looking at the reward here for G0, we only care about the action and state that we take in the first time step, right? Probability of action 0 given a0 and so on. Everything else here, we don't actually care about this when we're computing G0. But because we include these terms when we're doing our importance sampling, this can add to the variance, and this is actually a problem, right? So since this 99 factors are irrelevant, the thing is that how can we actually get rid of that? So I hope you understood this example, right? That when we're looking at G0 at time step 0, we only care about the action at time step 0 here because due to the discounting term there, all those future rewards we don't care about anymore. And all of this is just noise in this case, right? This is all just noise because we're not even looking at those actions and states anymore when we're computing our return. We're only looking at the current thing. So this is an extreme example. Of course, normally you might set your discount rate to be some value like 0.3, 0.4, 0.8, 0.9 or whatever. But still, this variance can step in when you start looking at action and states that are no longer important in the context of computing your return, but you're going ahead anyway and adding those terms to your importance sampling ratio, which you probably shouldn't do. So if we think of discounting as determining a probability of termination, or shall we say a degree of partial termination, then we can think of, say, or given G0, right? So we can think of it as partly terminating in one step uh, to some degree, say, say 1 minus gamma, right? And it will partly terminate in one step and only give us the result R1. And what's the idea here? Just think of it this way. Um, if someone says, what is the probability, so to speak, that we're just going to, given our discounting term here, right? Like, how does it affect uh, the probability that will terminate after one time step? Well, you might say if gamma is 0, then this might this probability may just be one that will only just get R1. If gamma is 1, then this is 0 because we're going to be going through the entire sequence. So that's how you can loosely think about it. But I'm going to show you, of course, like in more depth what I'm referring to here. So this is how we can look at it from, so as partly terminating and only giving us R1. And we can also think of it as partly terminating and giving us, so 1 minus gamma times gamma, and it gives us R1 plus R2, right? So again, so what we're saying here is, depending on our discount factor, right? If we have a return here, say R1, right? So what's the chance that we only get R1, right? And we partly terminate there because we don't care about everything else, and we're representing it by this term, 1 minus gamma. And then what's the chance that we get R1 plus R2 and then, just terminate like this after that, right? This is kind of like, this is the additional, partial termination term that we're adding here. So actually you realize that this is just a way of rewriting this GT, and I'm going to show you in a second why that is. But before doing that, I just want to show you the general formula when we're looking at our partial returns. So let me jot it down here. Like if we look at GT, which is equal to RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3 all the way up to gamma, say, final time step t minus 1 RT, right? This is how we define our return. But we can also define it in this manner, and think about this short discussion we just had about this, what we're calling our partial returns. So we can write this as 1 minus gamma times RT plus 1, right? Plus 1 minus gamma times gamma RT plus 1 plus RT plus 2 plus 1 minus gamma squared RT plus 1 plus RT plus 2 plus RT plus 3 all the way up to plus 1 minus gamma, and then we have gamma, here we have gamma capital T minus 2 just before the final time step. So this is RT plus 1 plus RT plus 2 all the way up to our final T minus 1. And then in the final time step, we multiply by gamma T minus 1, right? RT plus 1 plus RT plus 2 all the way up to RT. So essentially what we're saying is that we can rewrite the equation you see here, over here. We can rewrite it using what we see over there. And we call this our partial returns, right? These partial returns. And they are going to be helpful in becoming more aware of our discounts when we're doing importance sampling, right? So you can actually work through an example yourself to prove to yourself that this and this are essentially the same. Maybe pick a value for t like 3 and try to get RT plus 1 plus RT plus 2 plus gamma squared RT plus 3 by rewriting it in this manner. And this should be clear to you. So I'm not going to prove it here, but it should be straightforward doing that. So now we define something that we call flat partial returns, right? Okay, so let's try to underline it more properly here. So we have this flat partial returns where we say we define our return g from t up to some time step h to be equal to RT plus 1 plus, say, okay, in general RT plus 2 and so on. I'm just going to ignore the commas here. Say plus RH, right? Where we've got 0 is less than or equal to t, this is less than h, this is less than or equal to some final time step t, right? So what is this h, right? So we're saying flat because there's the absence of discounting, and partial denotes that these returns do not extend all the way, right? So this h is what we're calling the horizon. Okay, so that's what this h is. We're looking at the horizon because like we saw in that simple example here, for instance, h here would be equal to 1 because what we don't care when gamma is equal to 0, we don't care about those future returns, and we only care about the return, in this case in the initial time step. So we should make sure that our importance sampling ratio should only reflect this first term here. So when we talk about the horizon here, this is of course going to be dependent on what our discounting factor is, as that's going to affect how far into the future we should actually look at our returns when we're doing our importance sampling. So we define h as the horizon here. So now we need to scale the flat partial returns, right, by an importance sampling ratio, right, that is similarly truncated. We need to truncate the importance sampling ratio like we did here in this example, but we need a more general formula for doing that, because here we just showed an example where gamma was equal to 0. And we're going to be making use, of course, of this partial return equation that we showed over here. So let me just move on to the next page for this. So insert page after. So how are we going to do this? So let's actually rewrite. I'm going to rewrite this formula here, over here, but make it more general, right? So in general, we now compute our return, right? Return. How do we compute it? We say 1 minus gamma, right? And we multiply this by the summation from h is equals to, say, t minus 1 up to capital T minus 1 of gamma h minus t minus 1 times the return that we defined here as t up to some horizon h plus gamma times t minus 1 g t up to capital T. So what is this essentially? So when we define our return in this way, then we can scale our flat partial return. So if you see this first term here in this equation, so if we look at this, maybe use a different color this time. So if you look at this first term, this is simply corresponding to our equation until this point. And if we look at the other term, the final term here, so the one in pink, this is just corresponding to this final term over there, right? This is the idea behind this. So now that we have our return defined in this manner, the next step would be to weigh it with our importance sampling ratio, right? But being aware that we need to scale our importance sampling ratio based on this. So in order to do that, we say so V of S. So this is gonna be equal to summation. So this is going to be dependent on, for you to understand this, you need to have watched the previous lectures when we're talking about importance sampling ratio. But if you have, it should be fine, because we had defined what this capital tau S and everything here stands for. And I don't want to talk about it again, of course. So we have 1 minus gamma here, right? And then we have the summation from h is equals to t plus 1, from h is equals to t plus 1 up to t minus 1, right, of the same thing we have, gamma h minus t minus 1, right, times our importance sampling. So let me use a different color for this so that we can track things much more clearer. Yeah, let's use orange. We're going to have our importance sampling from t up to h minus 1, right? Okay. And then we're going to have our term g t up to h, right, plus gamma t minus 1, and then our importance sample from pt up to t capital T minus 1. So that's what we have here, and we multiply this by the final term, which is g t up to tt, right? This is essentially what all, and then we're going to divide this by the cardinality of our TS, the states that we're looking at here. And if you remember, of course, this equation is obviously for ordinary importance sampling. And if you want to do it for weighted importance sampling, I'm sure you can already figure it out. You just need to divide this by the weight. So the same equation here, you put it down there, but just get rid of the the GTs here, and you'll get the corresponding weights. And of course, you can easily figure this out yourself. So yeah, this finishes the discussion on how we can be more aware of our discounting terms when we're doing importance sampling in this context, to make sure that we don't add a lot of variance or noise when we're computing our returns. And by becoming aware of this, it actually helps us compute more accurate returns that will lead to, of course, having better algorithms. So this actually this is where I'm gonna finish this lecture, and in the next lecture we are gonna start talking about some more interesting topics such as temporal difference learning. We're gonna start looking at stuff like Q-learning, which is a concept that formed the heart of reinforcement learning. But given everything we've discussed so far, you realize that most of these algorithms, they really, I don't want to say they look the same, but once you get the hang of how one of them works, it will be much easier to understand the rest of them, because they are all based on the same fundamental concept that we've been looking at so far. So having said that, I'm going to end the lecture here. Thank you so much.